Elasticities along the demand curve. The elasticity of demand varies along most demand curves. On downward sloping linear demand curves that are neither vertical nor horizontal, the higher the price, the more negative the elasticity of demand. Consequently, even though the slope of the linear demand curve is constant, the elasticity varies along the curve. A 1% increase in the price causes a larger percentage fall in the quantity demanded near the top left of the demand curve than near the bottom right. Where a linear demand curve hits the quantity axis, open parentheses P equals 0 and capital Q equals A, close parentheses, the elasticity of demand is epsilon equals negative B times open parentheses 0 over A, close parentheses equals 0, according to equation 2.22. The linear pork demand curve in figure 2.9 illustrates this pattern, where the price is 0, a 1% increase in the price does not raise the price, so quantity demanded does not change. At a point where the elasticity of demand is 0, the demand curve is said to be perfectly inelastic. As a physical analogy, if you try to stretch an inelastic steel rod, the length does not change. The change in the price is the force pulling at demand. If the quantity demanded does not change in response to this force, the demand curve is perfectly inelastic. For quantities between the midpoint of the linear demand curve and the lower end, where capital Q equals A, the demand elasticity lies between 0 and negative 1. Colon 0 is greater than epsilon, and epsilon is greater than negative 1. A point along the demand curve where the elasticity is between 0 and negative 1 is inelastic, but not perfectly inelastic. A 1% increase in price leads to a fall in quantity of less than 1%. For example, at the original pork equilibrium, epsilon equals negative 0.3, so a 1% increase in price causes a quantity to fall by negative 0.3%. At the midpoint of the linear demand curve, P equals A over 2B and capital Q equals A over 2, so epsilon equals negative B multiplied by price over quantity equals negative B open bracket A over 2B close bracket divided by A over 2 equals negative 1 superscript 12. The linear demand curve hits the price axis at P equals A over B and the quantity axis at P equals 0. The midpoint occurs at P equals open parentheses A over B minus 0 close parentheses divided by 2 equals A over open parentheses 2B close parentheses. The corresponding quantity is capital Q minus capital Q equals A minus B open bracket A over 2B close bracket equals A over 2. Figure 2.9, the demand elasticity varies along the demand curve. On a linear demand curve, such as the pork demand curve, the higher the price, the more elastic the demand curve. Epsilon is larger in absolute value, a larger negative number. The demand curve is perfectly inelastic, epsilon equals 0, where the demand curve hits the horizontal axis. is perfectly inelastic where the demand curve hits the vertical axis and has a unitary elasticity, epsilon equals -1, at the midpoint of the demand curve. We have the standard price on the vertical axis, quantity on the horizontal axis. We have from the midpoint to the top part of the graph, the midpoint is unitary, epsilon equals -1, and it is elastic to the vertical axis where epsilon is less than -1, and it is inelastic from the unitary point and center where epsilon is less than 0 but greater than -1. At prices higher than at the midpoint of the demand curve, the elasticity of demand is less than -1. Epsilon is less than -1. In this range, the demand curve is called elastic. A 1% increase in price causes more than a 1% fall in quantity. A physical analogy is a rubber band that stretches substantially when you pull on it. In the figure where capital Q equals A over 5, the elasticity is -4. So a 1% increase in price causes a 4% drop in quantity. As the price rises, the elasticity gets more and more negative, approaching negative infinity, where the demand curve hits the price axis. It is perfectly elastic, superscript 13, which reads, the linear demand curve hits the price axis at P equals A over B and capital Q equals 0. So the elasticity of demand is -B P over 0. And as the price approaches A over B, the elasticity approaches negative infinity. And intuition for this is convention. And an intuition for this convention is provided by looking at a sequence where -1 divided by 1 over 10 is -10, -1 divided by 1 over 100 is -100, and so on. The smaller the number we divide by, the more negative the result, which goes to negative infinity in the limit. At the price A over B, where capital Q equals 0, and a 1% increase in P causes the quantity demanded to become positive, which is an infinite increase in quantity. The elasticity of demand varies along most demand curves, not just downward sloping linear ones. However, along a special type of demand curve called a constant elasticity demand curve, the elasticity is the same at every point along the curve. Constant elasticity demand curves all have the exponential form capital Q equals capital A P to the power of epsilon, equation 2.23, where capital A is a positive constant and epsilon is a negative constant, is the elasticity at every point along this demand curve. By taking natural logarithms of both sides of equation 2.23, we can rewrite this exponential demand curve as a log linear demand curve. The natural log of capital Q equals the natural log of A plus epsilon times the natural log of P, equation 2.24. For example, in the application, aggregating the demand for broadband service, the estimated demand function for broadband services by large firms is capital Q equals 16p to the power of negative 0.296. Here capital A equals 16 and epsilon equals negative 0.296 is the constant elasticity of demand. That is, the demand for broadband services by large firms is inelastic, where 0 is greater than epsilon and epsilon is greater than negative 1. We can equivalently write this demand function as the natural log of capital Q equals the natural log of 16 minus 0.296. Natural log of P is approximately 2.773 minus 0.296 natural log of P. We have figure 2.10. It shows several constant elasticity demand curves with different elasticities, except for the vertical and the horizontal demand curves. The curves are convex to the origin, bend away from the origin. The two extreme cases of these constant elasticity demand curves are the vertical and the horizontal demand curves. Along the demand curve that is horizontal at P superscript star in figure 2.10, the elasticity is infinite everywhere. It is also a special case of a linear demand curve with a zero slope, B equals 0. Along this demand curve, people are willing to buy as much as firms sell at any price less than or equal to P star. If the price increases even slightly above P star, however, demand falls to 0. Thus, a small increase in price causes an infinite drop in the quantity demanded, which means that the demand curve is perfectly elastic. Why would a demand curve be horizontal? One reason is that consumers view one good as identical to another and do not care which one they buy. Suppose that consumers view Washington state apples and Oregon apples as identical. They won't buy Washington apples if these apples sell for more than Oregon apples. Similarly, they won't buy Oregon apples if their price is higher than that of Washington apples. If the two prices are equal, consumers do not care which type of apple they buy. Thus, the demand curve for Oregon apples is horizontal at the price of Washington apples. The other extreme case is the vertical demand curve, which is perfectly inelastic everywhere. Such a demand curve is also an extreme case of the linear demand curve with an infinite vertical slope. If the price goes up, the quantity demanded is unchanged. D capital Q over dP equals 0, so the elasticity of demand must be 0. Epsilon equals, open parentheses, D capital Q over dP, close parentheses, open parentheses, P over capital Q, close parentheses, which equals 0 times, open parentheses, price over quantity, close parentheses, equals 0. A demand curve is vertical for essential goods, goods that people feel they must have and will pay anything to get. Because Sydney is a diabetic, his demand curve for insulin could be vertical at a day's dose, capital Q star superscript 14. More realistically, he may have a maximum price, P star, that he can afford. Thus, his demand curve is vertical at capital Q star up to P star and horizontal at P star to the left of capital Q star. Figure 2.10 is constant elasticity demand curves. These constant elasticity demand curves, capital Q equals capital A times P, vary with respect to their elasticities. Curves with negative finite elasticities are convex to the origin. The vertical constant elasticity demand curve is perfectly inelastic, while the horizontal curve is perfectly elastic. In the graph, we're giving price per unit. On the vertical axis, capital Q units per year. On the horizontal axis, there's one curve that's the lightest. Has a epsilon of negative 0.5. There's another line that's darker. It starts further to the left than the previous one, and curves closer to the horizontal axis is the epsilon equals -1, and the other graph starts furthest away from the vertical axis and comes closest to the horizontal axis, which is epsilon -2, and the horizontal axis is epsilon equals -infinity, and the vertical axis is epsilon equals 0, and P star is the intersection point of all three demand curves. Solved problem. Show that the price elasticity of demand is a constant epsilon if the demand function is exponential. Capital Q equals capital A times P to the power of epsilon, or equivalently log linear natural log capital Q equals natural log capital A plus epsilon natural log P. Answer 1. Differentiate the exponential demand curve with respect to price to determine the derivative of quantity with respect to price, and substitute that expression into the definition of the elasticity of demand. Differentiating the demand curve, capital Q equals capital A P to the power of epsilon, we find that d capital Q over dP is equal to epsilon capital A P to the power of epsilon minus 1. Substituting that expression into the elasticity definition, we learn that the elasticity is d capital Q over dP multiplied by P over capital Q equals epsilon capital A P to the power of epsilon minus 1 multiplied by P over capital Q equals epsilon capital A P to the power of epsilon minus 1 P over capital A P to the power of epsilon equals epsilon. Because the elasticity is a constant that does not depend on the particular value of P, it is the same at every point along the demand curve. 2. Differentiate the log linear demand curve to determine d capital Q over dP, and substitute that expression into the definition of the elasticity of demand. Differentiating the log linear demand curve, natural log of capital Q equals to natural log of capital A plus epsilon times the natural log of P. With respect to P, we find that d open parentheses natural log of Q close parentheses over dP equals open parentheses d capital Q over d P close parentheses divided by capital Q equals epsilon over P. Multiplying this equation by P, we again discover that the elasticity is constant. D capital Q over dP multiplied by P over capital Q equals epsilon times capital Q over P multiplied by P over capital Q equals epsilon.